All right, we're live. And more control. Okay, so just to get this out of the way, employee of Columbia University. Columbia has and is in the process of receiving lots of research grants to develop STAN. Also, I'm a co-founder of STAN Group, a startup based on STAN for businesses. And according to Columbia policy, those two things together imply that such facts have to be disclosed in presentations such as this. So what are we going to do today, or announcements? So first of all, some of you may have seen, if you're following the STAN on Twitter or Andrew's blog or whatever, Facebook announced that it was using STAN internally. We'd actually known that for a little while. They sponsored the STAN conference that took place the first week of the semester, and they have an R package and a Python library called Profit that all use the same STAN code to make univariate forecasts of a variable, what it will be in the future, using the STAN algorithms. And by itself, that doesn't mean a whole lot. Anyone who was paying attention already knew that STAN was just a great leap forward in terms of technology, but I think things like this cause more people to pay attention and hopefully become aware of it. And so this Profit R package, it only has like a couple models in it, but in some ways it's similar to what the RSTAN ARM package that we talked about on Tuesday tries to do. And that someone who's familiar with the STAN and the STAN language and knows how to make it work pretty well provides an interface in a language that more people are familiar with, such as R or Python, whereby they can cause the model to be estimated with just like a couple lines of code, specifying the variables and things like that. And these sorts of things are definitely necessary, and there have been more and more of them the past few years. When we started STAN, there was none of that. You just had to do everything in the STAN language, and it represented a steeper learning curve for people trying to use STAN. And so now that we have not just wrappers from from interfaces like R and Python, but actual R and Python package that come with a few specialized models, I think it opens up STAN to be used by more people. Now, it's not entirely free, because you're only allowed, with those packages such as Profit or RSTAN ARM, you can only estimate the models that are implemented, and that's up to the creators of those packages. You can only take advantages of the options that are offered to you. And so it's not as if you're going to have complete flexibility to use any prior distribution you want. You're only going to be allowed to use the prior distributions that are exposed for that particular function. But nevertheless, there's a pretty big segment of the sort of quantitative population that can understand kind of at a general level what Bayesian inference is all about, and can do stuff in a language like R that they're familiar with, but they're not necessarily going to invest the time to really learn how to use STAN in depth in the STAN language and all the tricks and stuff that you have to do. And so, without these things, they wouldn't be able to take advantage of STAN. With them, hopefully they can at least estimate some common models and use STAN, take advantage of the benefits that the Bayesian approach offers relative to frequentist inference and data mining, those sorts of things. And hopefully also, and we've seen this a fair amount, that once people use things like RSTAN ARM or Profit or BRMS, which we'll learn about after spring break, and start to understand that it can be easy to do, Bayesian estimation, then, maybe at that point they take the next step and actually learn how to do stuff themselves in the Stan language. So that's really what we're going for with packages such as these. But, Profit was the first one in Python to do something like that. There's about 12 or so in R that offer various models. So aside from that, we're going to start learning about generalized linear models today. And these are a generalization of the linear models that we talked about on Tuesday. Generalized linear models includes Logit models, Probit models, Poisson models, etc., that entail a transformation from the so-called linear predictor to the conditional mean of the outcome. And these are appropriate when the outcome is not just, have a sample space, all real numbers, could be discrete, could be counts, could be binaries, could be strictly positive numbers, something like that. And we have to use these transformations to ensure that the model meets some kind of minimal coherence for a data generating process. And the reason why there's a couple reasons why they're called generalized linear models. But back, in the 1970s or so, it was actually pretty difficult to do models that had these internal transformations going on in them that map from, all real numbers to something that's appropriate for the outcome you're modeling. And then it was discovered that there was a whole class of models based on the exponential family of distributions where, you could do this, the optimization would work reasonably well. You could get standard errors and consequently p-values and confidence intervals and things like that from this class of models called generalized linear models. And they quickly became pretty popular in the frequentist literature. From a Bayesian perspective, it's maybe not necessary to draw these distinctions between generalized linear and linear models or other sorts of nonlinear models that are not generalized linear models. All you're really doing is specifying your beliefs as to how the data are generated, deriving what the likelihood function would be in that case, specifying your prior beliefs about the parameters that go into that likelihood function, and then getting the posterior distribution. Now, historically speaking, we could only do that reliably for a lot of these models once Stan came along. And so these transformations, they not only provided a hurdle for frequentists to be able to figure out what would be the standard errors from a frequentist perspective in a model like this, they also often made it harder for Bayesians to get going because the most common thing Bayesians would try to do from the 1990s until about 2010 would be to write down a Gibbs sampler. But all these nonlinear transformations made it very difficult to derive what the full conditional distribution of this parameter, of that parameter would be in recognizable forms that we know how to simulate from. And you could do generalized linear models with Metropolis or Metropolis Hastings, but that never did really work particularly well. And so people kind of shied away from it. With Stan, it's usually not a problem estimating any sort of differentiable model, whether that's linear, generalized linear, nonlinear, involving ordinary differential equations, all kinds of things. Stan just doesn't care for the most part, and that's really good. It makes it easy for you because you can pump the parameters through all these nonlinear transformations, get out predictions at the end, and then interpret it, the results with full uncertainty in terms of observed variables instead of these parameters that only really make sense in the context of a particular model. So I'll have more office hours on Monday than I usually do. I think I'll start those at 3:30. You can still sign up for those on Courseworks. And the third homework, which I posted on Tuesday, we'll have that be due a week from today. Give you a couple extra days to do that for those of you who have, midterms and stuff like that in your other classes going on. So questions about any of that?
Why is it harder to do something with these transformations exactly? Because
we don't know what the full conditional distributions don't take forms like chi-squared or gamma or things like that we know how to draw from that distribution.
So don't we simulate those anyways? Like we just don't know generally, like we said that.
Well, yeah, but a Gibbs sampler, you have to know what distribution to draw from. So this parameter has a full conditional distribution that's gamma with like this parameter and that parameter, in which case you could draw. If you just get like a whole bunch of math, then okay, it's some distribution, you could normalize it. But if you don't have an algorithm already in R or whatever you're using to draw from that unnamed distribution, then you're kind of stuck. And so, Stan is sort of the post Gibbs sampler, doesn't deal with full conditional distributions. It just makes proposals from the joint distribution. So you don't have to worry about, does it take this or that form? Other questions? Okay, so we'll start with models that have a so-called Bernoulli likelihood. Before we see the data, we could say that Y has a Bernoulli distribution. The Bernoulli distribution has one parameter P, and we're going to allow this parameter P to vary from one observation to the next rather than imposing an assumption that this P is constant across all observations. And so to make things simpler, when we were talking about Ebola, we just assumed there was this constant probability that the drug would cure you. But in most realistic situations, there might be some reasons why a drug would be more likely to occur one type of person and less likely to cure another type of person, et cetera. So in general, when doing models in the social science, we'll usually allow the probability parameter P in a Bernoulli likelihood to vary from one observation to the next. And so how might we specify P? Since it's a probability, it has to be between 0 and 1, and we're going to specify for each observation that PI is some CDF, really, used to transform another unknown, eta I. And so we'll talk in a second about the different CDFs that could be used here. We're not really thinking about the CDF as telling us what's the probability that eta is less than or equal to, whatever. All we're really doing is using these CDFs as a transformation from all real numbers to the subinterval between 0 and 1. Okay, so Y is distributed Bernoulli with parameter P. P is equal to some transformation of eta that forces P to be between 0 and 1. Eta for each observation is going to be alpha times the row of X that corresponds to the ith observation times a vector of coefficients beta. And so this is going to be another deterministic transformation. And then we just have to put priors on the two unknowns, alpha and beta. Oftentimes we might go with like a normal distribution centered at 0 with a reasonably large but not huge standard deviation, particularly for alpha. And then, okay, if that's our sort of verbal description of the posterior distribution, we can write this down. We can take the logarithm of it. So we have the logarithm of some prior. And then the blue piece here represents the Bernoulli likelihood in log units. So we have the sum over the whole sample of yi times the log of the corresponding pi. Again, y is either going to be 1 or 0. If it's 0, then it doesn't really matter what pi is. If it's 1, then it just sort of accumulates up that sum. And then we have the other piece to the log likelihood, the sum of the observations of 1 minus yi. So that's going to flip around the zeros and ones times the logarithm of 1 minus p, which is the logarithm of the failure probability. So we can write this down in words. We can write this down in math. Ultimately, you're going to have to be familiar with both of those characterizations of a posterior distribution. So this Bernoulli model consists of a likelihood, which involves the Bernoulli. This transformation, which is known as the inverse link function from eta to p. For confusing frequentist reasons, this is historically, they'll refer to the link function, and that's the function from p to eta. But in terms of like thinking about this scientifically, it generally makes sense to talk about the function that maps from eta to p, which is technically the inverse link function. And then the final piece of a generalized linear model is this linear specification, at least in terms of linear algebra, for eta, which is what gets input into the inverse link function to come out with the conditional mean of the outcome variable. Recalling that for a Bernoulli random variable, the conditional mean is the probability, or the mean is the probability of success. The expectation is the probability of success. So this inverse link function here, mapping from eta to p, in this case, like I said, could be any function that inputs any real number, because eta can be any real number, and maps it and outputs to the interval between 0 and 1. So we can interpret p as a probability in the context of a Bernoulli likelihood. And so that function capital F can really be any CDF whose sample space is all real numbers, but we're really not using it as a CDF. We're just using it as a function that provides a reasonable transformation when talking about what we want to come out of it, which is a probability. So there's different choices you could use here, a couple that are listed. One is the function 1 divided by 1 plus e to the negative eta, the so-called inverse Logit function. And so if you use that form for f, this whole thing, or at least the likelihood part of it, is called a Logit model. And that's implemented in essentially every frequentist software. You also have the option, particularly with Stan, of specifying priors on alpha and beta. But you know, people usually talk, if they're going to give a name to a model or whatever, it's going to be based on what the likelihood function is of the parameters. But if we used another CDF, such as like the standard normal CDF, we get a slightly different model, one that is a lot more common in economics, whereas Logit models are more popular in statistics. But if you use the standard normal as your transformation function, then you get a so-called probit model, which is also implemented in pretty much every statistical software. So there's a few other choices that are supported by the GLM function in R, and consequently by the RStanArm package and the functions that estimate models within that. You can read about those if you go to the help for the binomial family. The family in R is called binomial. It's a little bit more general, but remember, Bernoulli is just a special case of a binomial with one trial per person. So Bernoulli is subsumed by the binomial family. Any questions about how we write down a Logit model?
So like there's the Bayesian approach, which is specifying the posterior,
Mm-hmm.
and then there's the frequentist approach. And these models you say existed before, also existed in the frequentist, so they have the link function.
Yeah.
So how did they interpret that differently from, like, how do they interpret the posterior? So like, because it seems the posterior is what is needed for this kind of inference.
Right. Well, so I mean, when frequentists were doing this model, they would just have the first three lines here,
Right.
which characterize the likelihood function. And then they would find the values of the parameter that are the mode of the likelihood function. So they literally didn't worry about the posterior distribution, or how to draw from the posterior distribution. Insofar as they would say anything, remotely Bayesian, they would say, well, for large samples, the sampling distribution of the maximum likelihood estimator is multivariate normal. For large samples, the posterior distribution is also going to be the same multivariate normal. So at least in large samples, it wouldn't be so bad if you used, maximum likelihood to obtain point estimates of alpha and beta, used the curvature of the likelihood function at alpha and beta to estimate the variance covariance matrix of the estimates, and then used that point estimate and that variance covariance matrix as approximations to a multivariate normal posterior distribution for alpha and beta. But for the most part, frequentists didn't even do that. They just sort of interpreted their confidence intervals as if they were Bayesian posterior intervals and things like that. So the differences are with the Bayesian approach, you at least have the option of specifying prior information about alpha and beta. You can oftentimes get away with using improper priors here, and the posterior distribution will still be proper. That may not be the best idea, but you'll see it be done. And then the big difference is that rather than finding a particular point, which is what frequentist algorithms do and what data mining algorithms do, MCMC Bayesian algorithms will try to draw from the entire posterior distribution in such a way that the proportion of draws in this area and that area are consistent with the posterior distribution that you specified. And so you really get an entire description or entire function that you can describe your beliefs about alpha and beta after having observed y and x. And so it's really, like we talked about the first week or so, do you want to talk about your beliefs about unknowns, or do you want to talk about how this estimator would vary if you did the same thing over and over and over again? Yes?
If there's no new data updates, what does it need to draw from this posterior distribution?
If you have no data?
No new data.
What do you mean no new data updates?
Like in the exercise, you know that new data equals null.
Oh, so that's if you're doing posterior prediction. Yeah, so that's, you can, once you've estimated this, then you can predict what the data would be, and you could do that either for old data or for new data or for data you don't even have yet. But that's posterior prediction rather than obtaining the posterior distribution. What I thought you were asking is, well, what if you have no data? In which case it's sort of technically fine, but all you're doing is drawing from your prior. That's what you believe about these parameters before you obtain new data to condition on. So you can do that. Other questions about this Logit model? No? Okay. So it talked about in the reading this idea of separation. And suppose you have some binary x variable, and for that binary x variable, it's always the case that y is 1 when x is 1. So when x is 0, y could be, different things. But when x is 1, every time in your data set, which may be a small data set, all the observations are always 1. And in that case, we say that separation occurs in the likelihood. And if we didn't have any prior information, we were just using the likelihood and trying to find the value of the parameters that maximizes that likelihood, our estimate of the beta for that binary x variable would diverge to infinity. So there's no value that, is no finite value that gives you an interior solution to this optimization problem. And that violates one of the assumptions that is necessary for maximum likelihood estimators to be optimal in a frequentist sense. And so under some assumptions that people don't talk about all that much, but are reasonably widely understood, there's no frequentist estimator that has a smaller variance in repeated samples than a maximum likelihood estimator. There's no unbiased frequentist estimator that has a smaller variance than a maximum likelihood estimator. But that, one of the assumptions is, well, the solution, the parameters that you're trying to estimate have to be on the interior of the parameter space. They can't be going off to infinity or going to zero if they're constrained to be positive, et cetera. And so when separation occurs, there's really nothing to say in favor at all of maximum likelihood estimates, and you'll probably get error messages or warnings if you try to do that empirically. What you can do if you're a Bayesian is utilize prior information about beta such that its posterior distribution, it might be pretty diffuse, but at least it's going to have like a reasonable range, and you have, you know, a possibility of using a Bayesian algorithm and at least getting it to terminate. And you can make inferences probably about the other parameters in the model. And so separation is one of the situations in which, you know, taking the Bayesian approach really does make a big difference. But if you don't, if you sort of specify that model and there's separation, but you don't have a proper prior on that beta, then even Stan is going to have difficulty. So the bottom line here is when you have separation, there's not information in the data alone to provide you a unique estimate of beta. Basically, any large beta is going to be adequate to capture this subset of the data, including a value of beta of infinity. And if Stan has to search like all large numbers, it's going to have problems. And so you do want to get in the habit of specifying at least reasonable prior on, you know, all the parameters in the model, particularly if you think that you might have problems such as this. And, you know, people are very, you know, in previous years, reluctant to specify prior information because it seems like, you know, you're just sort of opening yourself up to more criticism. And if that bothers you, then I find it's helpful to turn it around and say, instead of using the prior to specify what you think beta is, use your prior to specify what beta isn't. So it's not going to be 1 trillion or any number greater than 1 trillion. It's probably not even going to be in the context of like a Logit model. It's almost unheard of to see a coefficient in a Logit model be greater than 10. And so all these things that anybody who has any experience with is not going to find it, you know, too objectionable if you say, okay, I'm putting like, you know, a little bit of prior probability on the interval from -10 to 10 and not very much outside the -10 to 10 interval. No one should really have that severe an objection to something like that, versus if you say, okay, my prior is that this coefficient is, you know, 0.234 with a standard deviation of 0.01. Then, you know, you are, if you're trying to convince somebody else, probably not going to be very effective at that if they have a different prior belief than you. But, you know, no reasonable person really thinks there's going to be a coefficient in a Logit model of 20. It just doesn't happen. All right.
So would you just x is 1, y is 1 wherever x is 1 and 0 otherwise? Would you just remove x? Why would you?
Well, x is a valid predictor. You know, if I say, you know, a lot of times this comes up if you do like national surveys or whatever, you have like 2 people from Wyoming. And you ask, you know, people like, who are you going to vote for in the election? Both of them say Trump. And so you look in the data, and so whenever the like Wyoming variable is 1, the Trump variable is 1. And so you have this separation thing. But knowing the person lives in Wyoming actually, you know, tells you a lot about their political preferences. So no, I don't think you know, people do it, but it doesn't really make sense either to say, I'm not going to put the Wyoming variable into the model because, or I'm not going to put the state variable into the model. Now you're just failing to utilize one of the best predictors, you know, for a lot of things in like political science.
Does the separation means it cannot be converged?
Yeah, so the maximum likelihood estimate is not finite. And so these numerical algorithms that find maximum likelihood estimates, there's nothing for them to converge to except infinity, which is not going to happen on a computer. Right. Okay, so another thing you can do, and we talked about this a little bit last time in terms of this QR decomposition stuff. So in the stan_glm function in the rstan_arm package, the first thing you have to note is that internally, the columns of the X matrix are centered. So when you talk about the prior on the intercept in that, that's for centered predictors, and consequently, the alpha parameter in the you know, Logit model, Probit model, Poisson model, whatever, refers to you know, what you believe about the expectation of eta, because in the sample the expectation of X is 0. So that makes it a little bit easier to specify a prior on alpha because you can do it without reference to X. However, when you get the posterior distribution back, it's you know, you get this estimate of the intercept parameter, and that's for uncentered X variables. So with means that are not necessarily 0. This is to make it the estimates correspond to the estimates in GLM, at least when you have a lot of data. But we want to try, when, you know, doing Bayesian stuff, to make it as easy as possible for people to specify priors. And that tends to be the case when you can specify your prior on alpha marginally without having to worry about, you know, X. But specifying the prior on the intercept isn't usually that important compared to your prior on the coefficients. And so we talked about this on Tuesday in the context of stan_lm, but stan_glm also offers a reparameterization based on the QR decomposition. And so we said on Tuesday that any matrix X can be written as the product of two matrices, Q and R. Q is known as an orthogonal matrix because Q transpose times Q is equal to the identity matrix. Another implication of that is that the columns of Q are orthogonal to each other. And the R matrix is upper triangular. So if we substitute QR for X, then X beta becomes Q times R times beta. And if we let theta be equal to R times beta, then we can say, you know, in our specification for eta here, that eta is equal to alpha plus Q times theta. And so this is a reparameterization of the model where instead of using X and estimating the coefficients on those X variables beta, which those coefficients are going to be in the units of the corresponding X variable, what the rstan_arm package is actually doing is it's using Q to predict rather than X, and it's estimating these coefficients theta. And you might say, well, I don't want theta, I want beta. But once you have draws from the posterior distribution of theta, it's reasonably trivial to convert them into a posterior distribution for beta by pre-multiplying each of those draws of theta by the inverse of R to unwind the transformation. And so when you do this sort of thing in rstan_arm, what you get back, it doesn't even return you the thetas. It just uses the thetas to generate the betas and then throws the thetas away. So what you get back is parameters in the original model that you specified, but there was sort of an indirect step where kind of behind the scenes, although this is documented, Stan was actually drawing from the posterior distribution of theta and then converting it into a posterior distribution of beta. And so why might we want to do that? And the bottom line here is that sampling from the posterior distribution of theta is easier for Stan when it's using the Nuts algorithm. And that's because the columns of Q are orthogonal to each other. And thus, in the posterior distribution, the elements of theta are not very dependent on each other. At least, a priori, they're independent. That can change a little bit when you condition on Y. But for the most part, one value of theta doesn't tell you or restrict you that much for some other value of theta on a different column of Q. And so that yields a parameter space that's sort of slowly sloping. It's not changing too rapidly. And when you have these rapidly changing parameter spaces, that can make things more difficult for Stan to handle numerically, because it's got to be doing this numerical solution to the Hamiltonian equations. Like, you can imagine that shape that I put up previously when we were talking about Hamiltonian Monte Carlo, and just imagine it had all these like jagged edges and like roller coaster drops to it. That would make the whole thing be less precise to evaluate numerically in determining, where the next step of the leapfrog proposal should be. And so you can make things easier on Stan if you sort of set up a parameter space that isn't changing too rapidly. Ideally speaking, the second derivatives would be constant, although you don't have to, achieve that exactly. But this QR reparameterization really does make things a lot easier for Stan to get the posterior distribution of theta, and then all we have to do is pre-multiply that by R inverse, and now we have draws that represent our beliefs about beta, which is what we wanted, the coefficients on the x's. So if you're tempted to do something like say, okay, my prior on the betas is just going to be like standard normal or normal with mean 0 and some fixed standard deviation, you're usually going to be better off by specifying the QR equal true argument to the Stan underscore GLM function. That's going to turn on this reparameterization, and consequently the prior argument is now going to refer to theta rather than beta. But if you sort of have a diffuse normal centered at 0 prior beliefs about beta, then you can also have diffuse normal prior beliefs about theta. In practice, we actually do what's known, I guess you could call a scaled QR decomposition. Rather than using Q and R defined here, we multiply Q by the square root of n-1, and we divide R by the square root of n-1. And so now the columns of Q star are going to have a standard deviation of 1. And so if you did want to put an informative prior on just like one of the coefficients, but you weren't too sure about the other coefficients, what you can do is take that variable where you think you have some good information about its coefficient, put that first in your model. What the QR decomposition does is it just sort of rescales the first variable in X, and then it does a transformation to the second variable so that it's orthogonal to the first, and then it does a transformation to the third variable such that it's orthogonal to the first two, etc. And so it's really not doing very much to the first variable except rescaling it, in this case to have a standard deviation of 1. And so if you have, some predictor where like, the coefficient is going to be like pretty positive, make that your first variable, and then you can specify a normal prior on its coefficient that has, most of its mass to the right of 0 on the number line. It's very difficult to think about what would be a reasonable prior for the second, third, kth element of theta. But the first element of theta is only different by a scaling from the first element of beta. So you can sort of reason through that reasonably well.
These internals describe somewhere?
Not in Gelman's book, no. They are described in the R-stan-arm documentation. And I describe them now, like the vignettes and whatnot. So you don't necessarily have to understand every detail of this. But you should understand that if you're not going to specify an informative prior, you're usually on beta. You're usually better off doing this QR reparameterization and having it work in the space of theta. Once you do that, you don't have to like do anything else. It'll handle the transformation and the untransformation after the fact for you. So it doesn't change anything about your ability to make inferences about the betas. It just does it in a little bit of a more indirect way that makes things a lot easier on Stan. And so it really should be like the default should be QR equal true, but it's bad to specify confusing default arguments because somebody might come to it, think they're specifying a prior on beta, but if it's sort of defaulted to QR equal true, then it would be interpreted as a prior on theta, which is sort of surprising. So we don't do that. Question, Elka.
Why n has to minus 1?
Because of the estimator of the standard deviation uses n-1 in the denominator. So we're undoing that in order to have it be a standard deviation of 1. So how might we estimate a Logit model? There's a few in the reading. In this example, we're using a data set from the mass package on low birth weight or babies, some of which have low birth weight. So that's what the outcome variable is. Low is equal to 1 if the baby is considered to have low birth weight, 0 if it has a normal range of birth weight. We're going to model that as a quadratic function of the age of the mother. Here, I've sort of changed the units of age into 5-year increments just because, a 1-year change in the age of the mother is not really expected to have that much of an effect on the probability of a low birth weight baby. We're going to use the race variable, coding that as a factor. So this has 3 race categories that were measured. And the last one, which is really kind of the variable of interest, did the mother smoke during pregnancy? And if so, does that increase the probability that the baby would be born with a low birth weight? So that's specifying the model. It's all in the birth weight data frame. We're going to do 8 chains. The default is 4, but 8 is even better. To specify this as a Logit model, we have to specify the family argument. Like I said before, the binomial family is what you want to use when you have Bernoulli outcomes. And we specify link equal Logit. That's actually the default, saying we want to use the Logit link function. And finally, we'll specify QR equal true to do what I said previously. And so if you look at the output, you get estimates of all this stuff. These are posterior medians for the coefficients in terms of x variables. So it's already done the untransformation from theta to beta, and it's thrown the thetas away, and now you just have draws of beta. You can take the median of those draws, and you can put them here. Here, we see that the median of our beliefs on the smoking variable, or the coefficient on the smoking variable, is 1.1, suggesting there's a positive association between smoking during pregnancy and having a low birth weight baby. All right. So how would we interpret this coefficient on smoking, not just the direction of it, but the 1.1? So that's our median. But how would we interpret that? Nigel.
It increase, so smoking increases the log odds of having a low baby by 1.1, or you could kind of divide by 4. Again, it becomes 20%, 25%. Increased probability of having a low birth weight baby if you smoke.
Right. So in general, this coefficient on X refers to, how much eta would change if you had, a mother who didn't smoke during pregnancy versus one who did. But eta is only indirectly related to P, which is, the thing that we it's easier to wrap our heads around, the probability of having a low birth weight baby. And so with this inverse link function, it is correct that you can interpret eta as the log odds of the event, but no one really knows how to interpret log odds either. And this is a real problem, and a lot of frequentists just say, okay, well, it's positive and it's significant, so you probably shouldn't smoke if you're pregnant, without really being able to say anything concretely about how bad it is to smoke if you're pregnant. And this applies to all generalized linear models, and particularly in the Bayesian case, there's no reason why you really have to sit there and interpret a coefficient. What you can do is make predictions with different combinations of the X variables, map that in to the posterior predictive distribution, and it'll tell you how to interpret this nonlinear relationship between whatever variable and the thing that you can actually sort of describe, which is the probability of a low birth weight baby. So what we make here is a new data frame. We'll put in, some hypothetical ranges for the mother, and then, all three combinations of the race variable, the 0 and 1 for smoking, and then we call the posterior predict function. With our new data frame, we're going to get like 4,000 draws from the posterior predictive distribution. We'll take the mean of those column-wise, which is going to tell us the expectation or the expected probability of a low birth weight baby for each of these combinations of the predictors. I put some code for doing this, but don't worry too much about the details of how to make this plot. What I'm telling you is you can always make this plot, and you'll be able to say what's the relationship between age and the probability of a low birth weight baby. So what we have here, the black line is for race is 1, which I'm pretty sure is white people, and the probability of a low birth weight baby sort of increases in the early 20s and decreases after that. So the solid line here, this is for a woman of whatever age who's white and does not smoke. But for the same combination of race and age, the dotted line represents the probability of having a low birth weight baby for a white woman of this or that age who does smoke during pregnancy. And so you can see the probability, for someone who's like 25 goes from, maybe 0.15 up to let's say 0.35. And so you can just say the difference in probability for a white woman who's 25 years old who smokes, the difference in probability of having a low birth weight baby is 0.2 more than if she didn't smoke. And that's something that you can explain to like anybody. If we look for a particular age holding the smoking status constant but with a different race, so I'm not sure what 2 and 3 signify, but basically, being non-white has a similar increase on the probability of a low birth weight baby as smoking does for all sorts of health related reasons, lack of access to prenatal care, other stuff like that we would probably want to model more specifically, but we've sort of let it get captured by this race variable. So if you can make the posterior predictive distribution, you can always put, you know, something understandable on the vertical axis, something understandable on the horizontal axis, and show the relationship. For a generalized linear model, that relationship is going to be nonlinear, which means you can't just say, okay, the slope of it is this, the slope of it is that, because the slope of it changes depending on age and all the other variables. But you shouldn't have any difficulty generating and interpreting a plot like this because it doesn't involve any log odds or anything like that. Well, indirectly it did, but you transformed out of the log odds into probability space, which is something that, you know, everybody ought to be able to parse pretty well. All right. So there's a lot of stuff in the Gelman book about interpreting, and I would say don't interpret this except as just like a quick look, because one, this is just the medians. You need really to be evaluating the whole posterior distribution. Two, this is the coefficients for eta with respect to x, and we don't care about eta. So use the fact that you can get a posterior predictive distribution. You know, you can take the means of it if you want, or, you know, other ways representing the uncertainty, and talk about the relationship between things that are like quasi-observable, and, you know, talk about probabilities rather than talking about log odds and things like that. All right. So don't spend a whole lot of time interpreting. Use that time plotting. And then it's going to be pretty self-evident what the relationships are that are implied by your model. Questions? Yes?
You didn't specify any priors in alpha and beta for this.
I used the default priors on alpha, which is like normal with standard deviation of like 2.5. I can't remember exactly. I used the QR equal true. So technically I was putting a default prior on theta, which is also like normal. So yes, I could have been more explicit about those. But we have like 200 observations here. The priors not making that much difference. Yes?
So if we, as our X, plug in something more or less resembling a distribution of mothers in the actual population, and we plot this, and we report the results somehow, so if we like to plot, like, we'll end up reporting something that's analogous to like an odds ratio for the population, right?
If you want an odds ratio, you could get one.
Okay.
But, you know, normal people don't.
Okay.
I mean, doctors do sometimes.
So you're describing it as something like saying, okay, this, like the, sorry, I don't know what the race represent. Like,
yeah.
Race 2 is twice as likely or something.
Yeah. So, but, you know, if you want to talk in terms of ratios, you know, you can say, okay, for someone who's 23, whatever race 2 is, has twice as much probability. So if you want to talk about in terms of ratios, that's fine. I would say it's better to talk about ratios of probability than ratios of odds, because then there's like a double ratio in there. But yeah, I mean, you can do whatever you want. The Bayesian thing gives you the flexibility to do that, because, you know, if you just do the frequentist, well, you can make these lines, or not these lines, but lines, but they're not posterior means. They're just point estimates that were found to be, you know, the mode, and then you pump those point estimates through and multiply them by coefficients. Here, we actually got the whole posterior predictive distribution and then took the expectations of that. So you can legitimately say, like, I believe on average that someone who's 20 and white and does not smoke has like this probability of having a low birth weight baby. All right. Rolling on. So Poisson models, these are often used for outcomes that are a count. So non-negative integer is the sample space for y. Before we see the data, it's fair to say maybe that they are distributed Poisson. with expectation ui. Again, we're going to allow these conditional expectations to vary from one observation to the next. And since the expectation of a non-negative integer has to be a positive real number, we're going to use the anti-log transformation to map eta into mu. And then what is eta? Eta, as usual, is this linear predictor as a function of the x's. We can say, improper prior on alpha. And, maybe we want to have a student t prior on the coefficients. This is going to be, kind of concentrated near 0 by default, but have longer tails. So putting more probability on the chance that you get like a really large value for beta. That may or may not be appropriate, but we can write this out in terms of math by taking the logarithm of the kernel, and we're going to get an expression like this. And in the blue piece, that's where the Poisson likelihood comes if we map through all these transformations. Notice that when we take the logarithm of the kernel, that partially undoes the fact that we did the anti-log transformation to get from eta to mu. Whenever you have these sort of canceling transformations, it's good to do that yourself, because if you sort of do one transformation on a computer and you do the inverse transformation on a computer, you theoretically get back to the same place. But in practice, there's going to be numerical inaccuracy in both of those steps. It's also going to take longer. But we'll emphasize that more when we start doing these in the Stan language ourselves in April. If you want to do this in Stan ARM, all you have to do is call Stan GLM with a little bit different arguments. So this PTL is the number of preterm labor events that the woman has had up till that point. So it could be 0 if either it's the first time she was pregnant or she's been pregnant before, but the baby was born normal time, or it could be a relatively small count, like 1 or 2, if she'd had other children that were born prematurely. We got the age variables. Now we have an interaction between HT, which is hypertension, and smoking. We got the race variable. It's the same data frame. Now, instead of saying family equal binomial, we're going to say family equal Poisson, because we want the Poisson likelihood for these counts. And we're going to specify a prior on the coefficient to be, student t with 3 degrees of freedom, which is actually going to have pretty heavy tails. In this case, I didn't specify QR equals true because I really wanted this prior to refer to the elements of beta rather than introducing theta. But pretty much all we've done here is change the family from binomial to Poisson. And now we're estimating a Poisson model. A little bit different priors, but same basic idea. We get out draws rather quickly from the posterior distribution of this model. And we get results that look like this with the posterior medians. So, how would you interpret the coefficient on the smoking variable? Everybody. Yes. So we could spend another 5 minutes talking about, okay, smoke 1.2 for someone who doesn't have a history of hypertension. The expected difference in eta is 1.2 units higher for someone who smokes than for someone who doesn't smoke, for people who have the same age and race or whatever. But still, we're talking about eta, which is the logarithm of the expectation of the count. So yeah, that's going to be hard to interpret. So what we're going to do is make a plot. Same sort of thing we did before, draw from the posterior predictive. But here, so I draw from the posterior predictive, and then I evaluate whether that's greater than 0. So the plot I'm going to put up next is telling me the posterior probability of someone having any preterm deliveries. And 1 minus that would be the probability of never having a premature birth. We can make a plot like this. I didn't remember what all the dotted and dashed lines mean, but the idea of it again is race equal 1, I'm pretty sure, is for whites. And so you have this increasing as you get older, but fairly low for race 1 and race 2 of having, preterm birth. The solid lines, I'm pretty sure, are for people who do not smoke. And the dashed lines, one way or another, represent the probability of, for someone of that race who smokes and having any preterm deliveries in their life. So the vertical axis here is the probability that y is greater than 0, since this is a count that we're talking about. And so that's exactly, the sort of question that you can answer with the posterior predictive distribution and plotting and manipulations thereof. You couldn't even come up with that number, straightforwardly or any way you could put it on a plot with some frequentist thing. One, it's not a posterior distribution. It's this predictions from a sampling distribution. But two, to be able to accumulate, that's another like nonlinear function that would make it really difficult to go from like point estimates to, saying something about the probability of someone ever having preterm labor. Okay, so make the plots. I'm glad you're already catching on this, but pretty much anything that's not a plain linear model that has any sort of a nonlinear mapping going on in it, it's difficult at best to interpret those things. Difficult at best, even if you know the correct interpretation, to explain it to someone who does not. And way faster to like mess around with the plotting thing to get something like this, which even for someone who doesn't know anything about Bayesian inference can say, okay, as you get older, you have a higher probability of ever having a preterm delivery. Not particularly controversial, but we can actually say something about like how fast that probability increases as you get older or smoke. Questions? Make the plots. The Poisson model, like we talked about Poisson distribution, in this case we're talking about conditioning, but the expectation of y conditional on x for a Poisson is equal to the variance of y conditional on x, and that's kind of a cool property of the Poisson, but not something that we really often observe in the real world. But if that assumption holds, if you take y, subtract mu, and divide by the square root of mu, those sort of standardized residuals should have a mean of 0 and a standard deviation of 1. And if you do the Bayesian approach, you can IV estimate whether that assumption seems to be supported under your model. And the way we would do that is use the posterior linpred function, which spits out the posterior distribution of eta, unless you specify transform equal true, in which case it's going to give you the posterior distribution of mu. You subtract the outcome variable, or subtract mu from the outcome variable, divide by the square root of mu, and you get this thing which I'll call z, which ostensibly should have a mean of 0 and a standard deviation of 1. You can look at its quantiles. So this does seem to be kind of a little bit skewed in the positive direction, but particularly so when you look at the standard deviations, which are supposed to be 1, and like even the bottom 20% are having this standard deviation of like 1.6, and you know, at the extreme 80%, you know, it's well above 1, where you know 1 sort of corresponds to the assumption being true. So we're going to talk about these posterior checks more on Tuesday, but they're pretty easy to do, and you can say, okay, the assumption of the Poisson model is not supported by the posterior distribution I obtained from estimating a Poisson model. So what can be done in that situation? You can estimate what is known as a negative binomial model, again using Stan_GLM function. This is a slight modification of the posterior distribution we were talking about before. Now mu I is equal to gamma I times e raised to the power of eta I. Eta is the same as before, but we have this new parameter gamma, which has a gamma prior, where both the shape and the rate are equal to 1 over nu. So remember, the expectation of a gamma random variable is shape divided by rate. And so this is enforcing that the expectation of gamma is equal to 1. But it can have more or less variance depending on what nu is. We don't know nu, so we're going to have to put a prior on it. In this case, unit exponential. There's some other choices you could make there. But the bottom line is, if you take the likelihood function, as we've described it here, and integrate out yi, then you get a new distribution that's known as the negative binomial. And I believe I did an example of that. There were no x's. We just had like a constant term. And I showed like if you do the integral, you get this new thing that's a negative binomial. And the thing about the negative binomial distribution is that it has the same variance as a Poisson, which is going to be e raised to the power of eta. But the variance of a negative binomial is larger than the variance of a Poisson. So it's equal to mu squared over nu. As nu gets large, then, or you know, if it gets increasing at the same rate, then it can approach a Poisson again. But in general, we often see sort of lowish values of nu, which corresponds to a data generating process that has more variance than what it would be consistent with a Poisson process. And so it's usually better to just start off, if you're modeling a count, with the negative binomial likelihood, rather than doing, you know, what I did before, which was a Poisson, and then finding that the Poisson assumptions don't hold. So the negative binomial is really just sort of a generalization. Its limiting case results in a Poisson, but its interior cases yield extra variance. And usually in the social sciences, when you're modeling some sort of account, that thing, no matter how good your model is going to exhibit over dispersion. Now, sometimes in the social sciences, you'll find a process that exhibits under dispersion. It has too little variance to be consistent with a Poisson data generating process. And in that case, you'd have to do something else. And in that case, you'd have to get beyond R stan arm. But most of the time when we do things in the social sciences, your models will have over dispersion, in which case a negative binomial can fix that problem, bring your assumptions in line to how the data are generated.
Just basically like, because the expectation is not equal to the variance,
Yeah.
fix that over dispersion, use negative binomial.
Yes. Yeah. So negative binomial has more variance than Poisson does, but the same expectation. So if you have already a model estimated with one of the functions in R stan arm, you can just call the update function to change its arguments. So now we want to use negative binomial _2 as the family. That's kind of a holdover because that's what the distribution is called in Stan. I want to do my QR transformation again. The negative binomial models can be a little bit numerically flaky, or a lot numerically flaky. It's a harder model to estimate because of the over-dispersion thing. So this is definitely one of these situations in which, you know, doing the QR reparameterization to make the elements of theta be more or less independent of each other can really help the model sample better from the posterior distribution. And, you know, we get stuff that's not too different from what we had before, but we've also estimated this additional parameter called reciprocal dispersion, which is our posterior distribution for nu, or for 1 over nu, I guess. So the fact that this is not on the same order as mu tells us that, yeah, there does seem to be a little bit of over dispersion going on, that, you know, it was a good thing that we estimated a negative binomial. However, the standard deviation in the posterior is also pretty large, about 3. So there's a considerable amount of uncertainty as to how much over dispersion there really is in this data set that only has 200 people in it. So you can estimate a negative binomial model. As usual, don't spend time trying to interpret, make a plot, and then the interpretation should be pretty much self-evident. The last thing that I want to talk about today is, well, oftentimes you'll get a question like, you know, how much of a difference do your priors make, or, you know, how much did you update your beliefs as a result of conditioning on the data? And there's a function in the RStanArm package called posterior versus prior that makes a plot that you can look at to answer questions like this. So some of the plots that I did today were just plain R plots, but actually most of the plots that you would do after estimating something in Stan, they come out as GG plots. So you can modify them by adding, you know, new layers and stuff like that. So I got rid of the x-axis here because it wasn't fitting on it. But anyway, so we have a plot over on the right which says, you know, under our prior beliefs, here are 50% intervals centered around the median. So you go to the sort of corresponding color. Green is the coefficient on hypertension. And you say, okay, my prior beliefs was there's a 50-50 chance it falls between the coefficient here and there. The true coefficient is between here and there. 25% chance that it's greater, 25% chance that it's smaller, etc. And I could do that for, you know, all of these. You can see that under the prior, the default prior, there's considerable uncertainty about the intercept. That's usually not that big a deal. And considerable uncertainty about the purple one, which is this reciprocal dispersion parameter. It's constrained to be positive, so under the prior, it can't be negative. Anyway, here we have sort of credible intervals under the prior. On the left, we have also 50% credible intervals, but these are now posterior intervals as a result of conditioning on the data. And now we can see we have much more precise estimates of like the race variables and stuff like that. It actually, the dot representing the median is too big, and you can't really see the endpoints of the 50% intervals. But the 50% intervals are very small for a lot of these. The posterior distribution of the intercept shifted way down and got more precise. The posterior distribution of the reciprocal dispersion parameter got, you know, more concentrated, etc. So you can see how your beliefs change as a result of conditioning on the data, and you can see, you know, how weak your priors were to begin with. And a lot of times you'll see like your posterior beliefs are much more concentrated than your prior beliefs were, which basically implies that your prior beliefs weren't influencing the posterior results nearly as much as the data did. And so this is, I'd say, another thing that's pretty easy to explain. And there's a function that does it for you. Questions?
Is this ggplot or base plot?
Base plot uses ggplot. So yeah, what comes out is a ggplot object. So you can do plus, like change the theme and all that. Yes?
On the previous slide. This code, if you mention INIT_R equals one.
Oh, that's just, yeah, that was somewhere. Sometimes you need to restrict the starting values to be, by default, they're between -2 and 2. Sometimes in order to have good starting values, you need to compress them to be between like -1 and 1. That's just to make Stan be more reliable. In principle, that doesn't matter, but it just pertains to the starting values of the algorithm. So we'll worry about that another time.
It is to control the parameter.
It shouldn't affect anything. It's just the starting values. All right. Okay, so see you on Tuesday.